right, we are live, Cameron and Mog. All right, everyone, welcome to another Beer and BS for 2020. Sit down a few panelists today. Apparently builders are busy and can't make it. So Dylan is an apology, and Sean, I don't know, is Sean MIA, Mog?
He's just hustling. Sean hustles. You know what he does.
Sean is hustling, but you know what? We've got three of the best here today, and we've got Cam presenting today for a topic that I think is going to be really interesting and pretty relevant to a lot of the people listening along today, given that a lot of us are now starting to use a substrate underneath our membranes, whether that's for a flat roof system or a low roof system or even just for external sheathing. So without further ado, I am going to throw it over to Dr. Cameron Munro to enlighten us on the moisture characteristics of ply versus OSB. Now, if anyone's got any questions, throw them in the chat. This is a open for discussion kind of forum, and we'll just get the conversation going either during or after Cam's presentation. Take it away, Cam.
All right. Thanks, Hamish. Okay, so ply versus OSB. This is specifically about that context that we seem to be increasingly doing where we're externally sheathing our building. So we're putting a substrate on the outside of our stud wall or perhaps on the top of our roof rafters, especially under a flat sort of roof assembly. And as many of us would be aware, heating-dominated climate like Tasmania, Victoria, many parts of New South Wales, that will be the cold surface in the assembly for much of the year, and therefore the critical surface for condensation. So it's critical for moisture management that we ensure whatever we put there, be it OSB or ply, is something that's not going to give us grief down the track. And one of the things that keeps coming up that I have in conversations with builders and architects and what have you is that OSB is more vapor permeable, is in some way superior in that sort of assembly than ply. And I don't think the evidence supports that argument. And so I want to present some evidence here that I think refutes that and suggests that in fact ply is a more reliable choice on the outside of our walls and roofs. And, if that argument is accepted, then obviously that has practical implications for builders because many of you I know are running around trying to find OSB, it being relatively harder to source in Australia at the moment versus ply. Okay, so let's jump in. So I think the first message is clearly that it's not about the material per se, it's rather about the system. And there's no real bad product as such, rather a product installed wrongly in a system. So depending on the climate, for example, putting a vapor barrier on the outside of an assembly in a heating-dominated climate is a bad thing. But that's not an indicator necessarily that the product itself is bad. It's rather that we have designed poorly or inappropriately for that climate. And the second point, of course, is generally speaking, if ply or OSB get wet regularly, then you're stuffed. So there's no dispute about that at the extreme. Unless we're using treated products, these are going to be problematic. So we're talking about some sort of intermittent wetting event that may occur, either liquid water or else perhaps lots of moisture buildup through vapor accumulation. So all of these engineered timber products are in some way related at the outset to wood. Wood, as we know, is a really useful structural product. It's essentially air. At least half of it is air voids, which is why it's relatively light compared to some other materials. As we go through the hierarchy from real solid wood through to something like plywood, where we've essentially skinned the timber, but we've still got these veneers of the original grain there, through to more engineered, more processed materials like, say, OSB, MDF, particle board, and so on, or ultimately paper, like the paper facer on a plaster surface, then as a general rule, we increase the moisture sensitivity. That as we move towards the paper at the extreme end, we have a product with more sugars in it, more available food for things like mould, more ability for moisture to rapidly deteriorate those products. So how can we assess the performance of these two products? So I want to tackle that from 4 different metrics or parameters. Firstly, what happens with liquid water getting in contact with these materials? What happens with water vapor? accumulating or travelling through these materials, mould resistance and rot resistance, which clearly are related to those first two. So let's start with wetting. So this is liquid water, say under a windowsill or something like that might get into our system and then roll down the outside of our wall, get past our WRB or our external sarking membrane. So this is pretty clear. So this is some photos out of a study done a good 25 years ago now by a group in Finland. Back at that time, that group were pumping out a lot of really good stuff because a lot of the mould models we use originate with that research group. And what this photo demonstrates is what we intuitively know. If you put a droplet of water on the surface of plywood, it very quickly seeps into that material and dissipates along the grain, just like normal wood. Whereas with OSB, it will tend to bead on the surface. It's much more hydrophobic because the resins, and there's also often wax within OSB, will make that surface hydrophobic and prevent that droplet of water being absorbed into the timber, which is obviously a good characteristic. And this is related to this notion of capillary suction, so water getting absorbed into the structure of the timber and then drawn through that timber. And this, again, is a graph from that Finnish study and illustrates over time what happened to the total mass of water per square metre that was accumulated within a sample of OSB and ply products. And in the blue lines here are ply, different ply options, and the sort of the black and the brownie, are they, or reddish type lines are different OSBs. We have two clear groups of product there. And if we look firstly at the first sort of week or two that these samples of water were submerged or sat on a pool of water, you get higher initial suction from the ply products, those in blue. So the plywood initially is able to suck in an awful lot of moisture, consistent with that photo we saw before and our intuition. But then over time, after the first week or two, that accumulation within the ply stabilizes, whereas that in OSB tends to accelerate. So the water now has got past the wax coating, deep into the resin, deep into the strands of timber that make up the OSB, and it's starting to accumulate. And the OSB is more likely to start to expand, creating further voids that allows more water accumulation. And so ultimately, after many weeks of exposure to that liquid water, you're getting about 3 to 4 times the water content within the OSB, with the exception of this one sample of OSB, which happened to be Canadian. So all the others were European, and then we had this outlier that behaved much more like ply. So why was that? Well, the researchers that did this hypothesized that the reason for that was the resin within that Canadian OSB, which was a phenol formaldehyde, rather than an MDI or something else, one of the other resin chemistries that were more commonly at that time used in Europe. So that points to one of the variables here, which is the type of chemistry of the resin that you're using will have an influence on the ability of that material, irrespective of whether it's ply or OSB, to suck up and absorb water. So we have two competing things here. The ply will initially suck up lots of water, but ultimately the OSB will store vastly more water than will ply. All right, let's go now to the more complicated part of the problem, which is the water vapour. So these are the molecules of water that are floating in the air around us all the time that potentially, heating-dominated climate in the winter will tend to diffuse or make their way out through our wall or up through our roof, and they will then reach our substrate, be it ply or OSB, and they're trying to drive their way out and through. And so the critical thing here, of course, is we're trying to make sure that we allow them those water vapour molecules to draw out through the assembly and not accumulate on the underside of that substrate. So diffusion can probably be best visualized by thinking of liquid diffusion as opposed to gaseous diffusion. So something like a beaker of still water, and the key being here is that the water itself is still. And if I put a colorant in that water, we all know that it's going to slowly diffuse across and stabilize across that liquid. Critical thing again, the water's not moving, and yet the dye molecules are moving, making their way through that liquid and creating an equilibrium. And then the key part here to all of physics usually is that everything is trying to reach an equilibrium. High pressure is trying to reach low pressure, hot is trying to reach cold. In this case, a concentration of dye is trying to disperse such that it's equally distributed through our volume of water. And vapour diffusion is exactly the same. If we have a wall and we've got, say, OSB, and we've got the interior of an assembly with high vapor loads, which would be typical in the winter case, we call that high vapor pressure. Vapor pressure is just like air pressure. With air pressure, you've got lots of air molecules compressed in close to one another. Vapor pressure is the same. All it means is that you've got lots of water vapor molecules in a given volume of air. And so those molecules are trying to drive their way out so that they can reach equilibrium, so that the whole system all has the same vapor pressure. So how do you measure vapor resistance of a material? And the standard test is ASTM, is the American Society for Testing Methods or something, is the E96 test. And in that test, it's essentially a cup. So you have a little cup, and in that cup, you either put water, or you put a desiccant, or you put a salt solution. And then you put the material that you're interested in testing on top of that cup. And so here we have some samples of OSB stuck on top of the cup. And then there's a paraffin wax, the yellow stuff, around the side of that material to completely seal it. And then you put it in a chamber for a period of time. There's a stable temperature in low 20s degrees and a 50% relative humidity. And if you have 50% relative humidity in the chamber, so above our sample, and say you have water in the chamber itself, then the average humidity across that material is 75%, give or take. If, on the other hand, you have a desiccant, so 0% relative humidity in that cup, then the average relative humidity across your material is roughly 25%. And then if you want to know what the vapor permeance of your material is at other relative humidities, then you can use these salt solutions, which create different relative humidities in the mixture and therefore different relative humidities at the sample. And so you can get yourself a curve. And so here on the right is just a whole bunch of these in a test chamber that's been left there for a few days. And the way you measure the vapor permeance, I didn't actually say this, is you weigh the sample. And you take out this cup every few days and you weigh it, because you know you put in 50 grams or whatever of water initially. If you take it out and it now weighs 45 grams, then you know you've lost 5 grams into the chamber. So it's quite a simple test, but quite cunning. And so if you do that experiment on a sample or a number of samples, as we have done here, then you can generate a graph of vapor resistance across different relative humidities. And so obviously, anyone on a podcast listening to this is going to really struggle now, because I'm going to present a whole bunch of graphs. But the data that we've got here comes out of Woofy, which many of you have probably heard of, the hygrothermal simulation software that's widely used to try and predict any moisture problems that might occur in an assembly. And so all of these lines here represent different plies and OSBs within that database. And then that database in turn is sourced from empirical research, so lab experiments, just like the wet cup, dry cup test that I talked about a moment ago, conducted by different laboratories across the world, North America, Norway, Sweden, Germany, and so on. And so the key characteristics we see in these curves always is that at low relative humidity, so when the air is very dry, the vapor diffusion resistance, so the ability of the material to stop vapor driving through, is relatively high resistance. As the materials get wetter and wetter, the relative humidity increases, so the vapor resistance drops. And that characteristic is the same as some of our vapor permeable membranes. So many will be familiar with products like Intello and so on. They have exactly the same characteristics, where the idea is that when the system is dry, low relative humidity, they're relatively vapor closed, and at high relative humidity, they tend to open up, for want of a better word, and allow vapor to drive out. The second message here is that at low relative humidities, the data is all over the place. There's a very large scatter between different products, even within the same category. So you've got OSBs that are relatively vapor closed, all the way up to relatively vapor open, by an order of magnitude difference. And when we go to higher relative humidities, everything tends to cluster together a bit more. And what I would argue is that what's happening at the low relative humidities doesn't really matter. If your wall is dry, who cares how vapor permeable your membranes or materials are? There's no water to get rid of. it doesn't matter. What matters is when the system gets damp. Say at relative humidity is up from, say, at least 60%, maybe closer to 80%, when there's a risk of mould accumulating, of condensation forming on surfaces. At that point, it's critical that your layers have appropriate vapor permeability. So a lot of this data comes from equivalent to that test I described a moment ago. You've got the dry cup test, so average relative humidity of 25%. That means you've got the desiccant in the cup. And at the other end, you have the wet cup test. So you've got water in the cup, 100% relative humidity, 50% in your chamber, and therefore an average of about 75%. So I can take that even further. So I can add some extra data. So what I've done here is use the same data that I had on that previous graph, but then added in data from data sheets for other products or out of other research reports or published journal articles that I've managed to find, where they've stated what the OSB or the Ply product was and the vapor resistance at that particular, at a given relative humidity, and plotted them all here. And again, there's a lot of variability. So that's a key message. Well, your particular product will vary. But we do see a clustering at higher relative humidities. If we try and do a curve fit to these, we tend to find that the Ply is generally less vapor resistive, so more vapor permeable at all relative humidities than are the OSB samples. Now, a better way perhaps to try and visualize that is within each cluster of relative humidities, I can look at the averages. So the diamonds here are the averages within each group, and then the lines running off from those diamonds are the error bars. So they give me an idea on the variability of the sample. And so what I'm looking at here just visually is the red, my plywood samples, or the blue, my OSB samples, on average have higher vapor resistance than one another. And generally speaking, the plywood has lower vapor resistance. It is more vapor permeable out of most of these relative humidities that have been tested in these samples. But let's focus on the high relative humidities because, as I argue, that's where this really matters. Oh, actually, sorry, let me jump on to one other thing first. So there's one brand of OSB we can buy pretty regularly in Australia, Egger, company in Switzerland, I think, or Germany maybe. And they've got some really good published data. And they've tested that, they've published that data for different relative humidities. And so that is in this data set, and you can see here. So I've just labeled that just to give you an idea. And it would suggest relative to many of my other samples, when it's dry, low relative humidities, this particular Egger product is relatively low vapor resistance. That's generally, we'd argue, less vapor resistance is a good thing, certainly in a heating dominated climate. But at very high relative humidities, up around the 75%, which I argue is when it matters most, that vapor resistance is actually significantly higher than most of the other samples there. And that's sort of getting to my point. So here I've just zoomed in to part of that graph, the bit that I argue that matters, above 70% relative humidity. And again, at all of these groups, the plywood samples are generally less vapor resistive than the OSB samples. They're more vapor permeable, and in some cases, significantly so. Now, one has to just draw a line through this data because it's experimental data. You always get scatter. But if we arbitrarily pick 75% relative humidity and we look at all our samples there, generally speaking, on average, our OSB samples have twice the vapor resistance of our Ply samples. And similarly, 80% relative humidity, same trend, different magnitude, and at 90% relative humidity. So if you give me a sample of OSB and a sample of Ply and you don't tell me anything about the product and ask me to guess which one of these two are more vapor permeable, I'm pointing at the Ply and saying that one, just because I have to work with, we have to work with what we have, which is often is a paucity of data. And then just out of interest, that Egger product is up here, so relatively high vapor resistance at these high relative humidities. Okay, so maybe at this point you're saying, yeah, all right, fine, that's all German OSB or North American Ply or whatever. We're different here in Australia. Everything's different here. And I say, okay, fine. So I've got here 2 bits of plywood bought in Australia here, a 12mm structural ply and some 4mm softwood bracing ply. The 12mm ply, when I got the pack, actually comes from a company called Sedati, which is Brazilian. So my first point is your Australian ply that you bought from your hardware supplier is not necessarily Australian at all. So this is a global industry. So let's test those. So what you can do, you can get an ASTM E96 test done, and it costs, get this, $200 to do it. So it's not a very cost prohibitive exercise. So every time I have these arguments with my builder friends to try and suggest that plywood is better, and they say, yeah, but we don't know because this plywood we're going to get is different and we just don't know, we won't take the risk. My response is, well, get a sheet of it, chop it up, send it off for testing, and you'll get a general idea. So for these two samples, where do they fit on that analysis? And they're here. So I just did the wet cup test for these, so a relative humidity of 75%. And we see that they fit within the cluster of all the other plywood samples I have. So they're not outliers. This amazing Australian ply product is in no way different to any other ply from anywhere else on the planet. And indeed, they are considerably more vapor permeable than the OSB within the samples. So that gives me confidence to say to builders that I'm working with, you can use those particular ply products. They're no worse than an OSB equivalent at the very least. A little tip, just as an aside, if you're looking up a product data sheet, the first problem, of course, is a lot of these materials don't publish a vapor permeance or vapor resistivity value. So that's your first problem. Some of them do. And this particular product, I've obviously blanked out the brand, does publish a number. And it's down towards the bottom here in green, water vapor permeability, wet cup, dry cup. We know what that is because we now know about the ASTM test. And it tells us it has a mu, or a vapor resistivity, of 30 wet cup and 50 dry cup. And you go, great, got my numbers. Problem is that this actually originates from a BS, or British standard, which in turn is related to an ISO standard and an EN standard and something else. All these standards seem to be interrelated. And what that standard actually says is this: the vapor permeability shall either be determined as the vapor resistive factor according to a test. This EN test that it's referring to is actually the same as the ASTM test. So it's saying you can actually do some real world testing and report that value if you test according to this particular standard. Or if you can't be bothered testing it, then just use the values in this table. So the key message here is the value, if you choose to use from this table, is in no way experimentally determined for your particular product. It's just a generic value. And so to my mind, it has no credibility. There's no reliable implications for a particular case. So jumping on a couple of other related things, because this might come up, it's not just vapor permeability that matters when you're looking at the vapor behavior of a product. It's also the sorption isotherm, which is the ability for the material to absorb vapor, both as it gets wetter and also as it dries. There's a hysteresis going on here. And there's not a great deal to say about this graph other than I've tried to, again, get all the OSBs and plies that I could find, cluster them together, and try and work out if there's a difference. And I think the message from this graph to me is there's not a great deal of difference. Or if there's a difference, it's between products, not between materials. We can't say definitively, or with any confidence really, that an OSB has a higher sorption ability than plywood or vice versa on this sort of analysis. Whereas I feel like we do have the confidence on that vapor permeability that I was talking about a second ago. So two more things just to talk about. So firstly, mold resistance. So what really matters, of course, is if our system gets wet, is it buggered? And how quickly is it buggered? This was an image from an experiment done by the University of Waterloo. I haven't actually got the original paper on this one, but this is referred to. I'll put the reference here if anyone wants to look it up, from Building Science Corp, where they had test huts in their lab near Toronto, and they had a wall that they sheathed with OSB and another one with ply. Same internal conditions, same exterior climate, and look what happened after X months or years or whatever. The OSB on the right is covered in mould, the ply is as good as new. So from that one sample, it suggests to you that there was lower mould resistance from the OSB. Related to that, in this woofy hygrothermal simulation, we can estimate the moisture content, and then we can run a mould simulation to try and estimate the mould growth. And here I've taken a sample of plies, using that woofy database of plies, on one south-facing wall in a Melbourne climate, and a set of OSBs and tried to estimate what happens to the mould growth. And what we see is in the winter, so we've got time on the horizontal axis. And so in the winter periods, which is sort of from June onwards or a little bit earlier, we get a growth in mould. So the mould index is on the vertical axis here. And then over the summer period, you get a drying. The mould tends to dissipate away, which is intuitively reasonable. But the key thing here again is, generally speaking, but not exclusively so, the plies in that database are predicted to have less mould growth than the OSBs. And the only outlier here is a Norwegian ply. And in the database, that doesn't have a redistribution function. So the database within WFI, some of the materials have partial data. And so you can end up where it's not actually modelling the full physics of the material. And that's what I would argue is happening with that particular ply that you can see here. There's an outlier. All right, so finally, we've got mould. I'm arguing that ply is a better material for mould resistance, generally speaking. And I haven't talked about timber species. And then finally, rot resistance. So rot, again, is a fungus-related thing. There's very little out there on this, it seems, from looking at rot of ply versus OSB. One study I found was from Latvia, I think. And again, they exposed some ply and OSB samples to a rot fungus. And that was a birch ply, so being Europe. And that experienced about a 1% mass loss over a good 4-month period, whereas the OSB experienced about a 36% mass loss. So a huge loss in mass of the material. So the OSB was far more susceptible in that test than was the ply. So sort of almost finally, don't believe me, ask this guy. Anyone who's into building sites will know who Joe Stiebrick is, but he's sort of famous for saying that OSB is the spam of woods. It once was wood or some variant on that. And I don't think he means that as a compliment to OSB. So just to conclude, again, both OSB and ply are fine. If you use them in the right system, you're knowing what you're doing, you've got the right climate, you can make them work. No doubt about it. But all else being equal, I would prefer to use ply than OSB for the reasons that I've cited here. Predominantly the vapor permeability, which I'd argue is on average going to be higher, and therefore it can dry more rapidly, and the more mould resistant, generally speaking, than OSB. Okay, guys?
To digest, given, I've been banging on about using OSB for a good 2 or 3 years now. And I know, Cam, we were talking offline before that we were almost going to use ply on a project recently, in that retrofit project that we're doing in Eltham. And we erred away from it because we didn't have enough time to get that test done. But yeah, super interesting. So just out of interest, when we're talking about ply, obviously ply can be made of multiple timbers, right? You can get pine, you can get Australian hardwoods, you can get Brazilian hardwoods, apparently, which is what most of our stuff is. When we talk about ply, are we talking about like the structure of the build-up of the material, so that layering, or does it also take into consideration the timbers that are in there?
So it's a system, isn't it, I guess, Hamish? So it's both the timber and also the resin. So what is the chemistry of that resin and how much is used? And just to your point about, Brazilian ply, it might be eucalyptus, that's in that ply. Because remember, eucalyptus is one of the most widely grown timbers. So what I always find hilarious is, if you get some Spanish ply or something, it might well have eucalyptus in it. But yeah, it's a combination of the two. And again, I keep coming back to this, that on average, if I don't know for a particular product, then I'm going to assume that ply is more vapor permeable than an OSB. And, if I go back to that data that we had there were very few instances where the ply for a given relative humidity had higher vapor resistance than any of the OSBs did. So I feel fairly confident that that's going to be the case, irrespective of the timber species, the resin, etc.
Cam, have you got any data?
You go, Brad.
I was going to say, Cam, have you got any data on the ratio of wood to resin between OSB and Ply?
Yeah, so I think off the top of my head, I think Ply it's usually about 2% or less, and OSB is anything from 4 to 5%.
And do you think that's where the impact is on the vapor permeability and the mold resistance?
Certainly on the vapor permeability, that's going to play into it because the resin is obviously more vapor resistive than would be the timber. On the mold resistance, I guess that could be part of it, but possibly also the timber species used and the way in which the timber is sort of ripped apart with the OSB. So, Hamish made this point, I think, before we started, that the one advantage of OSB is that you're using your otherwise waste material from the tree, the less useful bits of it. But that will also be disproportionately be all sapwood, the really young wood that's got higher sugar content and therefore is more mold available. So, I don't have evidence for this, but I'm hypothesizing, I'm suggesting that perhaps that would make the timber, the particular age and species of timbers using OSB, more readily available to mold than does the Ply.
There's a couple of questions so I'll just answer a couple of these questions in the chat before you jump in, Mog. I'll come back to you in a second.
Yep.
There is a question from Saul, and I guess I'm tipping that Saul might not be originally from Australia, but obviously building in Australia. And the question is, why is rigid sheathing, Ply or OSB not common at all in Australia? I've designed our own house with a 9mm ply over the whole envelope, but builders seem not to be interested in rigid sheathing at all. I can only answer it intuitively, Sol, from my side, and that is that it's just not what we're used to. I know that full sheathing is something that's practiced all over America and in a lot of parts of the UK and Europe. I just think it's just something that we haven't adopted. I think it's a great way to have a super strong building. And also, Cam, you could probably add to this, if you do a peel and stick layer on the outside, you can actually get your air tightness from the outside, and arguably not having to put it on the inside.
Yeah, I suppose the other, fully agree with that, Hamish. It just makes such a structurally rigid building if you just sheath the damn thing up. You do change the vapor permeance of the assembly. And this comes to things like these peel and stick membranes that, the other parameter way we measure vapor permeability is something called an SD value. It's kind of closer to what I would consider an R value in a thermal sense, because it's a function of both the material property and its thickness. So an SD value of a vapor permeable membrane like a Proclimber Extensana or a Mento is about 0.05 meters, measuring in meters. It's the thickness of air equivalent vapor resistivity. So the shorter the length, so it's equivalent. So something like Extensana is equivalent to 0.05 meters, so 5 centimeters of air. And so you can imagine if I'm a vapor molecule trying to cross 5 centimeters of air, that's pretty easy. If I have to cross 20 meters of air, that's going to take me a lot longer. And so something like those vapor permeable membranes around that 5 to 10 centimeters, something like your plywood or your OSB is at least 5 meters. So as soon as you whack the sheathing on the outside of your wall, you're changing the vapor permeability of that assembly. And what you do in terms of membrane, generally speaking, doesn't matter so much anymore because the whole system is dominated by that sheathing. And so this debate about the vapor permeability of Ply versus OSB is absolutely relevant in that context, because that substrate is going to dominate the behavior, the vapor characteristics of the wall. And the part that then follows from that is, if you can't make the vapor permeability of the Ply, say, any lower, which you often can't do, in a particular climate, you need a vapor control membrane on the inside of that assembly, which is where we get the talk of all these, so-called intelligent membranes, like your Intellos and whatever, that are on the inside of the wall to try and stop that vapor accumulating on the back face of that substrate to start with. So if we're going to sheath our walls, probably fine without thinking about it in, say, Sydney. If you're going to try and do that on Cradle Mountain or Mount Buller or somewhere super duper cold, then you need to think far more carefully about the vapor control strategy that you're going to adopt, be that an internal air barrier vapor control layer or HRV, etc.
Brad or Mog, do you have any comments around externally sheathing homes as chippies?
When you do it, it's sensational. You say you do a flat roof system, places that solid, it braces the place up so much better, and it's such a dream to work on. It's in the climate that I build in, if you're not putting insulation externally, you need the intelligent air barrier, and it's a whole thing. Like, I drove past a site the other day in Launceston, and they had a steel portal frame. The whole house was steel. Then they just smashed ply over it, put a microporous membrane down, and had tiny little counterbattens. It's like, oh, we know that's going to be mouldy, but with the proper build-up, like Cam's saying, and that's kind of a question I had. If you're using an intelligent air barrier and you have the proper build-up, doesn't matter, because really the only time that it is vapor permeates is those few days where in my climate in Tasmania, is those few days of back diffusion, have maybe, a couple of weeks of it in summer.
It sort of falls out in the wash at that point, doesn't it, Mould? It doesn't matter if you use Ply or OSB if you've got the rest of the system dialed in.
Hey, Mould,
Yeah,
just for those who don't understand what back diffusion is, could you just explain what that means and when it might happen, and what I guess
Yes.
that you might experience to have that back diffusion?
So what we commonly see in parts of New South Wales, Victoria, South Australia, Tasmania, is inside the air molecule is fat with moisture molecules attached. As it goes through the insulation, it cools down and condensates at the dew point. But what happens in summer, when in the afternoon it's 30 degrees outside, you get the rain in the afternoon. The opposite happens, because you've got the aircon inside, so that moisture is fat and dense outside, and it comes through, and it, like Cam was saying before, it wants to make an equilibrium, and what happens is it ends up coming through your vapor permeable membrane and into your wall, and that's where your intelligent membranes will open up and let it into your house to be dealt by your ventilation strategy. But yeah, like, if you're using, like, if it was, say, in Queensland or in the tropics, that's happening all the time. So that's when you're using something like a DA on the outside, an air barrier on the outside, and where solid sheathing is, probably beneficial, but you really also want to have something that's not mould sensitive, because it's happening all the time.
How did he go, Cam?
Yep, and I'd probably just add like a heavyweight wall, like a brick wall or a sandstone wall if you're in Adelaide or whatever, or a reservoir kiting. When they get rain on them, they're like a sponge and they absorb that water, and the sun comes out, it drives that moisture inwards, and you just risk that accumulation if you haven't got your system right.
That's a side subject, and maybe a subject for another day, but we do all this about ventilated cavities, and we've got cavity closers that have got open areas, and we do for lightweight cladding, and then we go to a brick wall and we've got a 50mm cavity and we've got weep holes down the bottom. Like, and that's probably more susceptible to moisture ingress because it's such a porous product, and we just send it and think it's a good thing. Like, for example, on my place, I've got like cast iron vents every second brick to get the airflow in, and so I've got the actual airflow, but then that's 2 courses up, and then 2 courses down, I've got my weep holes for drainage. But it's just something you don't see often at all. It's, because it's bricks, we forget about it.
I had a note down here, Cam, because I read it in one of the graphs that Zip system was also tested, and it is, Cody's brought Zip up as well in the chat here. I've got a couple of questions around Zip, because we see all the guys from the Build Show throwing it on their outside of their buildings, and I think it's a great way to externally insulate and keep your frame warm, and then obviously you want to add some more insulation on the inside to get those R values up. Firstly, what are your thoughts on a Zip system in our climate?
So just be careful. I think they're to differentiate between Zip and Zip R. So
Yes. Yep.
Yeah, from what I understand, Zip is an OSB with a factory applied membrane, and the Zip R is also as that. Plus, it's also got probably
it's polyiso,
a PU or something. So polyiso, yeah. Insulation stuck to it as well to give you that additional insulation benefit. I can see it working. I mean, it's not, in a sense, it's not that different to what we're doing already. We're whacking OSB and Ply on and then a peel and stick. It can be very similar. I don't know. I didn't try to dig out the data sheet for OSB for its vapor permeates. I assume Zip publish it. One would hope they do. But it's...
I can get you whatever technical data you want from Zip.
It'd be interesting to have a look, wouldn't it? On the other hand, it's rather academic because we can't get it here. but maybe one day a supplier will come to market with something similar, because it sounds like it's got some constructability advantages for you guys on sites that are trying to whack these walls up.
There's a
With the
Cody. I hope that Cody, I hope that kind of answers your question about the zip stuff. He's also then just thrown in the chat here that there is another product called RAB from James Hardy, which, as far as he can tell, is a sheet of fibro with hydrophobic coating on it. Any thoughts on the vapor permeability of something like RAB compared to OSB and Ply?
Yeah, I have got a spreadsheet somewhere where I keep all those numbers, because there's for that. There's also Cineat do a thing called Weather Defense, the purple one, I think it's called. And there's a few other brands, I'm sure, of various sort of boards out there. Seem to be more targeting the commercial market. And they've got pretty good vapor permeability from what I remember, but I don't know the numbers off the top of my head. And I don't know what they do for structurally. Are they any good as a sheathing sort of?
I mean, I'm sure they're doing something, but intuitively, I think I'd rather throw Ply and OSB up, just because I'm used to throwing timber on or some kind of spam timber on my walls rather than a cement sheet product or a fibre cement sheet product.
Blaze have got a job that they've used that Cineat product because they're in flame zone.
I thought I remembered seeing it
that
not that long ago on Insta. Did they do a post on that last week, Brad?
Yeah, they've had a few little hits on it. Yeah, but I'm assuming that build up that they've got is predominantly to do with it being in flame zone. I don't know how much of an impact it's had on engineering, and it certainly seems here, from me spending a little bit of time banging around in the States, they think our engineering is absolutely ludicrous and out of control. And I don't think our engineers here are taking too much consideration of, how much structural integrity fully sheathing a building actually adds. They're just well and truly covering their ass.
It'd be a good thing if you could use it to get rid of the nogs too, wouldn't it, Brad?
I can't wrap my head around why in the US they can build completely with no nogs, concrete with no rebar, all that sort of stuff, and we can't.
Because the physics are different here, Brad.
Brad, I'm going to throw this. I'm going to throw this to you because I, firmly believe you're a far better carpenter than I ever have or will be. Like, if we're building with a 140 stud and you're just sheathing on the outside, so you're bracing materials externally, and you don't have your nogs running through, is there a risk of, I guess, our timbers twisting?
How stable
would you be concerned about that?
Conditions the timbers in, like in any house that
let's
we build.
Let's assume that it's let's assume that's one of our projects. And yeah, would you be comfortable not putting any nogs through?
Absolutely.
I'm sure it works.
When you're enclosing everything, the timber's at the correct moisture content, and it's going to be kept at a stable temperature, which it would be if it's close to passive house, then where's it going?
I guess I've been doing it for so
house.
long. I've over 20 years of, just putting nogs in just as a default. I don't know. It'd probably take me one or two projects to get away from it, but I guess I would trust your opinion on that one, Brad.
When I was doing my house, I almost struck up the conversation of pulling the nogs out because I've got horizontal battens on the outside and horizontal battens on the inside. I'm like, well, I put them in for the sake of ticking a box, and it took me 2 days to do it.
Yeah. I have done, so my background's volume. So I've straightened walls on houses that have barely got the fucking roof on. And it's the most pointless exercise because as soon as you take the face edge off the timber and it opens it up, they carry on like an absolute fucking pork chop. But since building properly, which has been quite a few years for me now, you buzz the walls once and I haven't noticed anything moving after that because everything's so stable. It's not getting wet and then drying, getting wet and drying. The temperature inside the house, even without insulation, is a hell of a lot more stable. So I can't see it really going anywhere, you know what I mean?
There is a question in the chat from Lucy, and I'll probably direct it over to you, Cam. And she says, based on this study, which I'm assuming is the information that you've provided today, are there any instances where you would recommend OSB used instead of Ply for the wall and roof bracing?
I can't think of. I think the only reason that OSB is popular overseas is because in those markets it's cheaper than Ply. That to me seems to be about, that and the environmental thing about using less all the offcuts from the tree are probably the only things that I can think of that are pros of OSB versus Ply. From a moisture point of view, Ply always wins in my book based on, those numbers that are illustrated there, unless someone can suggest to me where, another characteristic that I'm missing. But I can't see why I would want to use OSB if the question is, what do I do from a moisture management point of view?
Yeah, I think that's one of the hardest things.
Question, Cam.
Go, Mog,
You
fire
go,
away.
mate.
No, you go.
So I get a lot of people asking me, particularly about flat roofs. I do a lot of conversations around the ProClimate system, and I always get asked, "It's like, oh, can we use yellow tongue flooring?" And I say no, because it just seems like you shouldn't be using flooring out there. It seems very vapor closed with the wax and all that sort of stuff on it. We did have a little conversation before around it. What are your thoughts?
Is that to me, or can I jump in there?
Yeah, no, that's to you, Cam. Sorry.
Sorry. Yeah, so I say test it. Test it. $200. Test it. Bloody hell, I'll pay half. Jeez. I hate this speculation stuff. It's like, we can get this stuff tested.
There's four of us here. We all chipping in $50 a head, and we'll do it.
Right, who's got an off-cut kicker?
I reckon the next Beer and BS, we actually charge for it, and then we just get a pool together, and we'll just get all of the products that we can think of, and then send them all off to get tested, and then we got the answer for it, and then you can just go for ham and use whatever you want.
And again, to be fair to
performance membranes, stuff like that.
And to be fair to anyone who might be skeptical, yes, it's only one test point on one particular parameter, but it is a critical one, and it provides us some degree of confidence, or not, that this particular product we're holding in our hands is not in some way bizarro. Because whenever we do something like woofy, invariably, other than the membranes, we've got no idea what the brick characteristics are. We've got no idea what some of the timbers we're using in these walls are. And so we're having to make guesses. We're using a proxy. And so if I've got one data point for my yellow tongue, I can go into the woofy database, look through all the particle boards there, find something that has a similar characteristic at that test point, and say, well, that, on the balance of probabilities, that seems to be as close as I'm going to get. To be fair, I could be off, but I've got to make decisions based on what evidence of data I've got, and then you can test your product. But, we did have this conversation before the call, because I did send a sample of a structure panel, so a similar sort of particle board, off for testing, and it was, relatively vapor permeable, and it was very close to another particle board in woofy. Because I said to the client at the time, because they were going to sheath the outside of their walls and their roof with this stuff, I said, well, we ought to get it tested to give us at least some degree of confidence that when I test it and model it in woofy, that particular particle board I'm choosing is in the ballpark to what you're using there. But I keep going back to this. It's like, do we really think an Australian particle board manufacturer is doing something completely unique on the planet? That they've invented their own resin in their secret chemical laboratory that is uniquely different to everybody else on the planet? Or that they're using a timber species that's completely freaky? Like, it comes back to this Australian exceptionalism things. They're no different to anybody else.
It's the only flooring product that I've seen. I'll get to that in this same one, Haim. The only flooring product that I've seen that's exceptional compared to anything else is Advantech from Zip, like Huber. Every other particle board, whatever it is, the edges swell. It's fucking dreadful. That's the same shit. Yeah, Saul said, what are your thoughts on a wall system with 140 mil stud frame, 9 mil ply, tape seams of boards, a basic wrap, vertical vent batten, cladding batten color bond? Will the ply with tape seams be an adequate airtight layer? I'm going to say no, it won't. 9 mil ply is generally not that airtight. We're really dependent on the ply. And if you're going to take the joins on the ply, why wouldn't you just take the joins on the wrap and have something that is guaranteed to be an airtight layer used as your airtight layer rather than guessing?
And you've still got to add a membrane to that assembly anyway.
Well, he's got a basic wrap in that build up anyway.
Yeah. So,
and you can achieve airtightness with a relatively cheap wrap. I did 0.42 with the cheapest wrap that Benjamin Obdyke offers. So yeah, so it's all about how you detail it, not the product itself for airtightness.
And just from
great flex, Brad.
From a moisture point of view too, I think there's a few things you haven't mentioned there. So like, what's the climate Is there an internal vapor control layer? Is there a HRV? Things like that. Is there something weird going on in the house? Is a client going to have tropical fish tanks and a sauna or something? So many different parameters at play.
Yeah, I get this is probably like one of the
You
hardest things
do-
as a builder.
You go, mate.
Yeah, this is one of the hardest things as a builder. Like, obviously, like we break some of these sessions down to, you know, treated pine versus not treated pine, OSB versus ply. But realistically, when we're sitting down to plan a build, you know, we're asking these questions at every step, you know, and there's so many things. So it's not just a, you know, like why would we use OSB over ply or ply over OSB or whatever, you know. This is what I really like about this BS and beer stuff. It's like, here's all these other questions that we should be asking before we arrive at the answer.
Totally. What were you going to say, Mob?
I was going to say, if you do use plywood on say a flat roof system and you're using a stick back membrane, what happens with the plywood is the fur stands up when it gets wet. So you really want to sand it. Ideally you install it and then wrap it before it gets wet. But if it did get wet, it needs a sand. Otherwise you'll get little air bubbles all through it if you're using a stick back membrane. Just like a little tip. And then also with plywood, if you have it really tight together, you get expansion and contraction, and those stick back membranes don't have stretch. So whether that be maybe a 2 mil packer between the sheets or something like that to give yourself some expansion and contraction. Obviously with OSB, there's no grain, so it doesn't have a direction of swelling. So just a couple of little things to watch out for if you do decide to go plywood over OSB. But yeah, I thought it might just be worth putting. Like you look at, I've got it on my place actually. I've got a little porch that's got Adhero on it, but the ply got wet and I didn't sand it. And I was like, oh, no, it should be right. But it bubbled like straight away. It was a tiny little piece. I was like, oh, so it's, I've made the mistake.
It's always good to learn from other people's mistakes, Mob, especially on your own home.
I've made plenty of
probably
them.
just one last closing thing that Brad has just answered Jess's question there, but I'll probably end on this because it's probably a really good thing to talk to everyone about. And Jess says, remember that water control layers are more important than air control layers for durability. Cheaper membranes aren't always as good as controlling water depending on the properties of the material. I mean, I know our default product is ProClimber. I know yours too is MOG. Cam, you've demonstrated that you'd like to try other things sometimes, and same with you, Brad. But still great, or great products. So yeah, your Class 4 from Bunnings may not be the best solution to when you're wrapping a house properly. Does anyone else have anything to add, or is there any more questions before we wrap up for the day? I've just got a couple of kids that are looking at my office door here that I probably should go and attend to.
I was going to say, Amy, though, per Cody's question before about like some of these other rigid air barrier products like the rag board and Senior weather defense and stuff, I've just got up the data here, and they have got pretty good vapor permeability characteristics if you believe the data. Like I haven't actually listed in my spreadsheet here what relative humidity they were tested at, per my comment before, that when the system's dry, that most products have got much higher vapor resistance than when they're wet, but they're pretty vapor open. And so, conceivably they're good options. But again, I don't know what price point they land at and whether they work for, all of us on this panel work in resi construction.
Awesome. Well, thanks, Cam, for another really informative presentation. I mean, I think one of the things that I just love about getting you on to talk about this stuff is you break down really complicated topics and talk to everyone so I can understand them, which is hopefully so everybody can understand them. And if you do want to go back and re-listen to this episode will be sitting on the Mindful Builder Network's YouTube channel, probably about 3 or 4 weeks. And I might just take the opportunity now, just because I'm hosting tonight, just to remind everyone about an SBA event that we've next week. It's called the Retrofit Playbook. So if you're interested in learning more about retrofitting, which I think is going to be a big market for all of us, whether you're designer, client or builder, moving forward, given the state of the building industry with construction prices being where they are, it is an absolute must not miss that one. And it is available as a recording. So if you can't make it on the day, you can always just jump on and buy a recorded ticket, and it will get sent to you a couple of weeks afterwards. Anyway,
It's an in-person
Brad,
event,
thanks for jumping on at that short notice. It's an in-person event, yeah, in Victoria. All right, team. I'm gonna say goodbye to everybody and hopefully see you next month. Cheers.
Legends, thanks. See ya.
Yeah.